Alright, so we're going to build on our knowledge of the unit circle from yesterday, and eventually the goal here, usually at this point, we start solving trigonometric equations. I think we'll wait till next week or maybe the week after to do trig equations this time because of Park and various reasons. So we'll just look at inverse trig functions, then next week we'll start looking at graphs. We'll probably just be able to touch on them a little bit. So, inverses of trig functions. What do you guys see on the board notationally that tells you we're talking about inverses? Can you tell me? There should be something. The -1 superscript, right? That's what tells you inverses. So all functions have to have an inverse if you want to solve equations, because in order to get rid of multiplication, you have to be able to divide on both sides of an equation. In order to get rid of logarithms, you have to be able to exponential each side, raise it to a power on both sides. In order to get rid of square roots, you have to be able to square both sides. Those are all inverse operations. So the functions, sine, cosine, and tangent, which we're going to look at the graphs next week, you have to be able to do something to them to be able to solve equations involving them. Does that kind of make sense to you guys? So this is the key to being able to do that, as well as the key to finding angles. Because so far, we've always been provided with the angle in trig problems, haven't we? We're doing unit circle, we have to figure out where it's at and then draw the triangle or draw the point, right? When we were doing problems where we were solving for sides of a triangle, usually it said, this part of the triangle we measured at 15 degrees. This part of the triangle was measured at 30 degrees. But if you know how long things are, but you don't know what the angle is, this also allows you to do that, okay? It lets you find angles. So that'd be a good thing to write at the top of your notes if you want, as a guiding direction. This is all about finding angles. That's what inverses of trig functions, that's their most basic purpose, finding angles. Okay? Alright, so I'm just going to get us used to the notation and how to think about these first, because how you think is everything, pretty much. So, it's not always going to look like this when you see problems. You're not always going to see sine of theta equals a ratio. But even if it's not a ratio, you should be thinking about it as a ratio, because a trig function is a ratio. Does that make sense? All 6 trig functions, I introduced you them by calling them trig ratios, because they're opposite over hypotenuse, opposite over adjacent, etc. Right? So when you saw stuff, it was usually like this kind of thing, right? Sine of theta equals some ratio, tangent of theta equals some ratio. So now what we're doing is we're going backwards. We're saying if we operate on both sides, what does that mean? So it's kind of like I'm thinking about operating on both sides of this little equation with the inverse. And if you operate on both sides, what happens when an inverse operates on its original? They cancel out. Can you guys see that that canceled out and gave me theta? And then over here we have the inverse sine of A over B. It's on the opposite sides, but that's what happened here. So I'm even starting to think about equations from the very beginning. But when you see this, you're thinking about unit circle calculations or whatever. This is not so different. But as soon as you see arc sine, that's another way to say this, by the way. As soon as you see inverse sine, this can also be written as the arc sine. So a lot of the time in college algebra books or calculus books, you'll see that notation. So that's other notation, definitely want it in your notes. You'll see arc sine. As soon as you see either this or this sine inverse thing, your mind should automatically be thinking, they're asking me to find an angle. This thing's equal to an angle, like theta. Does that make sense? But as soon as you see this notation, your mind should automatically go to the angle place. They're asking me for an angle. I've just got to figure out which angle. Okay? I've just got to figure out which angle. So as soon as you see any of these notations right here, I'm going to be thinking angle. If you do that and you know your unit circle, nothing in this section will be difficult. Okay? So you're going to see a variety of different kinds of problems. One of the first ones, most basic, most important, which will also make you better at your unit circle, is ones that say, find all the possible values of inverse cosine of root 3 over 2. How do you read that correctly? You read that correctly as they want me to find an angle, or the angles, because they said all, right? There's probably more than one. Find all those angles that do this, that have a cosine ratio of that. And so if you're going like, man, that sounds really crazy, I'd have to like guess all day long, right? This tells you everything you need to do right here. Just draw. Use it as your guide. So all we are given is that the cosine has to be root 3 over 2. Let's draw a triangle that does that. Is that positive or negative? Positive. So I'm guessing one of the quadrants it might be in is quadrant 1, because it's all positive, right? Let's draw a triangle. You don't have to make your triangle to scale or anything. It might be nicer if you do. And see, this tells you how to label your triangle too. It says label the what? Root 3. The adjacent. Why the adjacent?
Because it's cosine.
Because it's cosine. So where should I put my root 3? To the right, hypotenuse, or bottom? That's the adjacent of this angle. I really want to find this angle. I don't know it yet, but okay. And where should I put my 2 then? Yeah, because cosine is adjacent over hypotenuse. All right. So have you seen that triangle before?
Yeah.
Mine's not to scale at all, but have you seen it before? What's this side usually? 1. Oh, opposite 1. What's always opposite 1? 30 degrees. That's from knowledge of the unit circle. That's why I'm saying you need to know how to do unit circle first. Yeah, you need to know your 30, 60, 90. So that's the answer right there. 30 degrees, because that's the angle that does this, right? They asked for the angle, we're going to give it to them. This is equal to 30 degrees, but we're going to write these in radians because that's how things work in trig. What is 30 degrees in radians? Pi over 6. That's one answer to this problem. They said find all the places that do that. All the places. This says find all the places that have a cosine of root 3 over 2. Pi over 6 is just one of them. Every coterminal angle will do the same thing, won't it? Every time if you went around again and got to the same place, or again twice, or 3 times, or backwards once, or backwards twice, any of those things would work too. So we're going to learn how to count with an infinite set right now. It's pretty sweet stuff. I'm starting to get excited. So pi over 6 plus, how far is it going around? I need radians though. Around in radians is 2 pi. 1 time around is 2 pi, or 360 degrees. And we said we could go around once, twice, 3 times, any number of times we want. So for a computer or whatever, you put a counter there. Let's call it K. Book might call it N, I think. Whatever. It's a counter. And then you say K is what? K is any integer. That means we could go around 1 time, 2 times, 3 times, -1 times, -2 times, -3 times. That says all the possible places that will have a cosine of root 3 over 2. Okay? There is one other quadrant too. We only have half the answers. Even though we've got an infinite number of answers right here, it's still only half. And you need that other half in equations. So, where's the other triangle that I can draw to do this? Carson?
In the second quadrant.
You think second quadrant?
Yeah.
All right, let's try it.
Be on the bottom.
Let's try it. You think on the bottom too? I think there's usually 2 spots. Sometimes there's just 1 spot. Most of the time there's 2 spots. Let's try Carson's second quadrant. Going from this, it says label this side root 3 and the hypotenuse 2. There's something wrong with that. What?
It's negative.
What should be negative here truly? The root 3, right? Isn't that left? Does this say negative?
No.
No, so that'd be a different problem. Where else is cosine going to be positive? 4th quadrant's correct. What's the quick way to know that, by the way, other than like, guessing around a little bit? Cosine, I think we learned yesterday, cosine is synonymous with which coordinate, x or y? So you guys haven't done enough practice yet. Cosine is synonymous with x. Where's x positive? Quadrant 1 and quadrant 4. That's why this goes in that quadrant too. Same sides, adjacent, hypotenuse. This is still 1. This angle is still 30 degrees, except what's 30 degrees down there? That's a different set of answers. I'm I'm going to have, you could write it two different ways. I'm thinking negative pi over 6, right? Go negative pi over 6. Or if you went this way, what would be all the way around to there? 6 sixths, 12 sixths. Back one is 11 sixths. I'm going to write this as 11 sixths. And every coterminal angle of that will also work. So plus 2 pi k. Okay? So there is all the angles that have an inverse cosine of root 3 over 2. Two infinite sets. Let's look at one more of those before we move on and do something else. So it seems like you guys definitely need another example. So what if they ask you for, I don't know, the inverse tangent of, let's say, 1, negative 1. Let's do that one. What are all the angles that have a tangent of negative 1? Start trying to draw. So, since it's just negative 1, your first instinct should be it's probably one of these edges. I don't think that works though, because tangent is y over x. And if you try to do one of these edges as y over x, you always get 0 or undefined. So that won't work. You could try it for a while. So what's another way I could write negative 1? In Trigland, usually you should have ratios. So you should write that as negative 1 over 1. So I'm going to write this as negative 1 over 1. Now Akash has already tried to guess the angle. You hear him up here? He said 45. I think he's got an idea. But let's just take it a little slower than that. Very nice. So negative 1 over 1. Where's that triangle going to be? It's going to be in the first quadrant? I think it's negative here, right? Should we just try here? Let's try it. So opposite, adjacent. Does that look right? No, but I think it's still in the right spot. Can't a negative always be transferred to the bottom? So then you can just go like this, and that looks right. Yeah, and that's still negative 1. Boom, there's an answer. What triangle is this? 1, 1, root 2. All I care about is what triangle it is. 45. It's a 45. So there's Akash's 45 that he's trying to say. But it's not just 45. This isn't 45. 45's over there. What's over here? Remember, we want to be in radians, so we're thinking in pi over 4s. So in terms of fourths, how many fourths are over there? There's 4 fourths. Back one is 3 fourths. Okay? So we've got 3 fourths pi. Every coterminal angle works, so I should put plus 2 pi k, where k is any integer. If you don't say what k is, you're not really correct. You need to tell a computer or a person what k means. It's a counter. Okay. Is there any other triangle where I can do the same thing?
Yes.
Should usually guess there's going to be another one. Kasha's got it. Carson, you have it too?
Yeah.
Which one?
It's going to be in the 4th quadrant.
4th quadrant? You guys think 4th quadrant? Why not the 3rd quadrant? Stuff's negative in the 3rd quadrant, right? You're going to get negative over negative here, which would be positive 1. We want negative 1, which we could make this negative and that positive, and there you go. So this will be the same angle, 45 degrees, except how do we say 45 degrees in the 4th quadrant? You could go backwards and say negative 1/4 pi, or we could, I hear it from other people, we could go 4 fourths, 7 fourths. Either one is fine. I'm going to just say negative 1/4 this time. It's probably an easier one. Plus 2 pi k. Any coterminal angle to that would also have a tangent of negative 1. Okay? So what's different about these 3 inverse trig calculations? What looks different? They all have capital first letters. Now this is something that our textbook does that is kind of unique, but I actually really like it. Because in reality, in future classes or any other textbook you have, there'll be no distinction between capital letters and small letters. But this gets you to think about what are called the principal values for these, because we just saw that how many answers are there for most inverse trig problems? There's like 2 branches, and each branch is an infinite set. Sometimes you'll just have one branch, you know. Sometimes there's just one place that makes it work. But there's an infinite number of solutions for those. When you see a capital letter, that's our book's way of telling you how a machine thinks about this, okay? That's our book's way of asking for what's called the principal or the first kind of answer, and it's just asking for one answer. Because, can you guys remind me, when you put one thing into a function, how many things are supposed to come out? Just one. So inverse functions work like that too. If you put one thing in, how many things can a machine tell you? Just one. So that's what we're going to learn how to do here today, is what the calculator would give you, kind of. And that really matters in terms of how to work with electronics and how to solve equations as well. So if you see a capital letter, they're not asking for all the things that can do that. They're just asking for the principal one that does it. Okay? So what is the principal inverse cosine of 0? We do this the exact same way, by the way. So we should draw, and we should say, okay, where does the cosine, what angle, this is still angles, right? What angle makes the cosine 0? Do you guys think it's going to be a triangle?
No.
I don't think triangles have side lengths of 0. It's got to be one of the edges, doesn't it?
Yeah.
So which edge? Well, then you say, okay, cosine was it x or y? Cosine was x. Where is x 0?
Pi.
It is 0 here.
No.
Yeah. X is 0 there and
Oh, X.
there, right? Those are the 2 places. That spot's 0, 1. That spot is 0, -1. But that's 2 answers, right? I thought we said when it's principal arc cosine, there's just one answer. And that goes back to these restrictions. Once we see the graphs, these restrictions, I think, will make more sense. So I'm going to go back and look at this section a little bit more once we see the graphs. So which one of these is it? Inverse cosine is restricted to the top half. So this is what angle up here, guys? What angle's right there? 90 degrees or? There we go. Half pi. Done. That's what your calculator will give you. You type that in your calculator. There's an inverse button on your calculator. As long as it's in radian mode, it's going to give you 1.57 blah, 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 blah. For 3.14 divided by 2. Okay? But you don't want to do this with your calculator. If you do, you're not learning anything. You'll be out of luck. So, you can check yourself, though. What about the inverse sine of -√2/2? What do you guys think? Is that a triangle, probably, or one of these edges?
Triangle.
Triangle. You think it's a 45, 45, 90. So Akash, notice, he has reflexes he's developed. He recognizes this. Let's do what we did last time. Which quadrant do you think it would be in if the sign is negative? Here?
No.
Sine's the y-coordinate, right? Is y going to be negative here? Y is going to be negative either here or here. So let's draw both those triangles. Sine goes opposite over hypotenuse, right? So let's label them. Opposite hypotenuse, or here it'd be opposite hypotenuse. Now those triangles look a little bit funny. They look a little funny, don't they? They have the exact 2 triangles we knew. That's why this recognition factor plays in. This is the rationalized version of something else. I've been talking about that a lot, right? What is this the rationalized version of?
-1/√2.
Yes. That's the same thing as -1/√2. Now, how good you are at recognizing this, if you look at these triangles and you're like, yeah, that's that 45-degree triangle, then you're good. Hopefully, though, you look at this and you say, hey, I've seen that before. That's the finished product of this. And if I labeled it like this, I went opposite hypotenuse, opposite hypotenuse. I bet that's making you feel a little bit more comfortable. What triangle is that clearly? So 45, 45, 90. Okay, we're asked for what angle, so what angle has this spot? Well, we drew it, so we just got to answer which one that is. For inverse sine, the one that works is in one of these two quadrants. So I'll make a note of that in a second. So it's going to be this one. So we're going to say negative pi over 4. That triangle. Okay? The inverse sine of 3/2. What do you guys think? An edge or a triangle? You might not be sure. It's a triangle, but as soon as you draw that triangle, you're going to be like, I've never seen this triangle before. That's a hint to you that something fishy is going on, and that has to do with these restrictions. So when you're doing inverse sine, when you're doing inverse cosine, when you're doing inverse tangent, inverse sine, the principal inverse sine, oh, I messed it up, lives in quadrants 4 and 1. It lives between the angles you'll get output, the range of inverse sine is anything between negative pi over 2 to pi over 2, anywhere in there. The range of inverse cosine is in these two quadrants, so its range is anything from 0 to pi. And the range of inverse tangent is the same thing as inverse sine, except the edges are open circles. So the range on inverse tangent is this. Those are the only answers that can ever pop out if you toss this in your calculator, if you toss this in there. This has to do with cutting the graphs of these to make them invertible, because you'll see, because of the repeating quality that we've been seeing with this coterminal angle stuff, when we look at the graphs, they cycle and they don't pass the horizontal line test. So you have to do something special, and this is kind of what that special thing is to make them invertible, so that you can even talk about their inverses in the first place, so that it's possible. So we'll talk more about that next week. Okay? But the whole thing here is recognizing that this says what angle does this stuff, and you making a little drawing and trying to decide where that angle is that will do this stuff. So I also made one other little note here. The domain, what you can put into these. For inverse sine and inverse cosine, having to do with the graph, once we draw the graph, this will be crystal clear. For inverse sine and inverse cosine, the only things you can put in are between negative 1 and 1. Zeros between negative 1 and 1, that's why we got an answer. Negative root 2 over 2, if you put it in your calculator, it's like negative 0.707. It works, so we got an answer. What about this one? 3/2 is 1.5. Put this in your calculator. Why don't you guys try it right now? Pull out your calculator, type in inverse sine of 3 over 2 and see what it tells you. Make sure you're in what mode? Radians, very nice. Just grab your calculator, type in inverse sine of 3 over 2, and you're going to see that it tells you, if you're watching the video, try it. It's going to tell you error. Make sure you confirm Noah. If you're just sitting there relying on Noah's knowledge, you're not learning. Noah's learning. This does not exist. It is undefined. And again, that has more to do with the graphs. So we're going to see exactly how this works, and we'll review it after doing the graphs. And it'll make a lot more sense then, but at least we'll have some legwork already done. Okay? All right, so I said one of the purposes, besides solving equations, which we haven't even gotten to yet, is using inverse trig functions to find angles. So it says we've got a painter. He leans a ladder, 30-foot ladder, pretty big one, against a wall. Safety guidelines, we all have to deal with government bureaucracy these days, right? Say the distance between the wall and the ladder should be 1/4 the length. And what angle should he make, or what angle is he making? Okay? So sometimes I make fun of these kinds of regulations because they're annoying, but then I once fell off a ladder because of not doing things like this before. It hurt a lot when you say that. So 20 feet down onto the ladder, broke a couple ribs, wasn't a good day. So how should I draw this? I've got a triangle, right? We've got a wall, really tall wall, a couple stories high. There's this big long extension ladder. I'm thinking this triangle probably is what we're dealing with, yeah? So this side's 30, right? That's the actual ladder length. And then it said the regulations say the distance between the walls should be 1/4 the ladder length. What's that mean?
Just one.
Are they trying to tell me this side or this side? The bottom, right? So the bottom should be how long then?
1/4 of 30.
Half is 15, 1/4 is 7.5 feet. Okay, we could find this side with Pythagoras if we want to, but that's not what they asked us, right? We're supposed to find the angle. What angle? This one?
No.
We know that one.
That one.
That one. What do you want to call it?
Theta.
Let's use the one we're used to, theta. So now I think we can write a simple little equation down and find theta. So what do you guys think? Should we use sine, should we use cosine, or should we use tangent on theta? Cosine. Because we've got the adjacent, and we've got the hypotenuse. There you go. So write it down. Cosine of theta is 7.5 over 30. You can reduce that if you want to 1/4, but I'm just going to leave it, okay? And then you want the angle theta. How do you unlock theta? You cancel out the cosine by using the thing we just learned, the inverse. On both sides, you do something to one side, you've got to do it to the other side, right? This cancels out, you get the angle you want, which is the inverse cosine of 7.5 over 30. I don't think that's one we know from our unit circle, so we should go to the calculator. Now, for touchy-feeliness, what do you guys think? What mode should your calculator be in? Radians or degrees? So this is where you got to be cognizant of switching. Most of the time we'll be in radians, but this time,
Degrees.
I think we want degrees. Yeah, so switch your calculator's mode to degrees and type in the inverse cosine. It's at the top of the calculator. It says mode. You see it?
Oh, yep.
And then one of the first options says radians or degrees.
I am already.
So be always aware of which mode you're in, because you'll need to be switching back and forth. I don't think it's quite 45.
7.5.
This 45 would have come out as something from the unit circle, wouldn't it, Akash? That would have been 1 over root 2. This was 1 over 4. But maybe pretty close. What did it come out as, guys?
75.52248.
So about that? Okay. Let's look at one more type of problem before we go today. Now that we know a little bit about inverses, let's use them for a couple things. So one of the things we're going to be able to use inverses for is to solve equations. These equations can become much more complex. We're going to start out with the most simple possible trigonometric equation. All right. So that is something like the sine of theta equals 2/5. So if you're trying to crack into the sine of theta and get at that theta, what do you have to do to get rid of the sine layer? That's how you want to think about this. What do you apply to both sides to get rid of sine? What we just learned, inverse sine. Inverse sine gets rid of sine, just like multiply gets rid of divide, just like logarithm gets rid of exponential. Inverse function. So I do it to one side though. I have to use it on the other side. These cancel out. Don't think of this as multiplication. It is not multiplication. You're putting one inside of the other. It's chomping down, and it chomps down hard enough to cancel on the left. So we get our angle is the inverse sine of 2/5. Now you can do this by hand or by calculator. What do you guys think? If we draw a triangle in the first quadrant, do we know a triangle that has 2 on one side, the opposite side, and 5 on the hypotenuse? I don't think we know that triangle. It's not familiar. So we're going to go to our calculator with this. And you guys tell me, for this problem, should we be in degrees or radians on our calculator? Degrees. How do you know? It says right there. Yeah, it's totally right there in the problem. It says make sure you're in degrees. So change the mode to degrees if it's not already. I always like to check. And have your calculator do that for you. So the inverse sine of 2/5. That's how many degrees it is. I think if we actually drew this triangle, it kind of makes sense that it's about 23 degrees up from this axis. I'm not going to. So my calculator says theta is approximately 23.578 degrees. This problem looks like it's identical. Isn't it? Isn't it the same problem? working equation. But
to 4 at the end.
this says I want an answer in a different spot. So to solve this, you do it the same way. You say I'm going to use the inverse sign on both sides, not multiplying, operating with the inverse. It cancels over here. I get theta equals the inverse sine of 2/5. I hand that off to my calculator, and it tells me the answer is 23.578. But then I'm like, dang it. 23 degrees is not between 90 and 270. So is there a triangle where you could get the sine to be 2/5? The same way. Your calculator is not smart enough to tell you that.
If you're in the fourth quadrant, or
So you think the fourth quadrant?
Sorry, the third quadrant, and it's negative over negative, then you're going to get a positive.
All right, so you can see Rachel's already thinking about other quadrants it could be in. Let's just draw our first one before we make a decision, okay? So 2/5, that's in the first quadrant, right? Where's our 23 degrees? I'm talking about right here. I should have drawn it in blue, sorry. Right there is that 23 degrees about, 23.578 degrees. Sine is the X or Y?
Why?
Sine's the Y. So if Y is positive, what other quadrants Y going to be positive in? Here, right? So I think if you draw that exact same triangle over here, so that its opposite is 2 and its hypotenuse is 5, that's the triangle that's going to do it. So the question is, how many degrees is it to go all the way over there? How do you figure out that little red arc? Because that's our answer. 180?
Minus 46 point, or I guess it'd be 47.
Why do you need to double it, Sean?
Because you've got 2 bits on each side, right?
Yeah, but I'm going from the beginning, right?
Yeah.
So I want this angle to be exactly the same, that 23 degrees, that those triangles are the same, except I'm starting from here and going all the way
Oh,
to
then I
that.
guess we subtract only 1.
So I'm just subtracting that. Does that make sense?
Yeah.
So that's going to be what? Can you guys tell me? 156 point what?
422.
422 degrees. That's the angle in quadrant 2, which still gives you a sine of 2/5. You can, of course, check that using your calculator. If you're suspecting your answer was wrong, it was a little too mysterious, check it. Say sine and plug it in. Plug in 156.422 degrees. I got to be in degree mode, and my calculator is going to say 0.399999. Is that close to what it's supposed to be? 2/5 is 0.4. Really close. And that's because we rounded. So we're correct. All right? So that's how you do that one.
What